If you're anything like us, you're just fascinated by the universe's most extreme physics, black holes, gamma ray bursts, things like that.
Mhm.
But, it's funny. The greatest cosmic threats, they aren't always the biggest objects. Sometimes they're the ones that pack the most terrifying power into the smallest possible package.
And that's exactly what we're diving into today. We're looking at an object that just fundamentally rewrites the rules of planetary destruction, the neutron star.
Right.
And this isn't about a simple impact. This is about the raw power of fundamental forces. We're talking gravity, magnetism acting over just astronomical distances.
So our mission today with this deep dive is really to pull together what the sources are saying and define the true scale of this thing, the mechanism of destruction.
Exactly.
We want to detail why astronomers see this as, and I mean this, literally the worst possible astronomical scenario. It's instant planetary scale devastation.
And it's governed by physics, not a slow process, just proximity. It's a study in extremes, really. We have to get our heads around not just what it is, but how it concentrates all that power.
Okay, so let's unpack the scale.
Yeah.
Because it's so deceptive, right? You hear star, you think massive.
Colossal, yeah.
But a neutron star is what's left over after a supergent star goes supernova. And the thing that remains is, well, it's tiny.
That is the absolute key. The collapse is so total, so complete, that what's left is minuscule by any cosmic standard. We're talking about a diameter of like 20 kilometers.
20 kilometers, so the size of Manhattan.
Or any medium-sized city, basically.
A city-sized object. But, and this is the part that's so hard to grasp, that tiny size holds a phenomenal amount of mass. More mass than our own sun.
Which is already 99.8% of everything in our solar system.
So how do you do that? How do you cram more than the sun's mass into something 20 kilometers across?
Well, you do it by destroying matter as we know it. I mean, the internal structure of atoms, this is where the physics gets just fascinating. In a normal star, you have gravity pushing in, but you also have thermal pressure and something called electron degeneracy pressure pushing out.
That's the force that stops electrons from piling on top of each other.
Exactly. It's a quantum rule.
Yeah.
But during the supernova collapse, gravity it overwhelms all of it. Everything.
So it collapses past that point, the electrons can't hold it up anymore.
Precisely. The electrons are basically forced into the protons. They combine, and what you get is this incredibly dense soup made almost entirely of neutrons.
A neutron soup.
And this is the aha moment, about the density. The sources all highlight this one fact. Just 1 teaspoon of this material.
1 single teaspoon.
Would weigh, here on Earth, approximately 1 trillion kilograms.
1 trillion kilograms. For a spoonful. I can't even picture that. It's like the mass of a huge lake compressed into a sugar cube.
And that's why it's so critical. That extreme density, that gravity, it defines the kill mechanism. Because with that much concentrated weight, you realize you don't even need a physical impact to cause total devastation.
Right. So the disaster is non-kinetic. You don't get hit by it.
Wow.
You just get destroyed by its fields, by the warping of space, just because it's there.
Its mere presence is the catastrophe.
Which, okay, that leads us to this whole idea of an invisible catastrophe. What happens before it even crosses our atmosphere?
Well, you have to think about the 2 big forces that act at a distance. Gravity and magnetism. Gravity is the one we all get intuitively. The neutron star's gravity is so immense, it warps space-time itself.
But you're saying the magnetic field is the more immediate threat.
Oh, by far. It's the more violent threat initially.
And why is the magnetic field so insane? Does that come from the collapse too?
Absolutely. It's like a figure skater, right?
Yeah.
They pull their arms in and they spin faster. When that huge original star collapses down to just 20 kilometers, it conserves its magnetic flux. You're squeezing a normal magnetic field into an impossibly small space.
And that amplifies it.
By millions, sometimes billions of times.
Millions of times stronger than Earth's magnetic field. An invisible force like that, just sweeping through our solar system. I mean, that has to react with our technology, right?
It's beyond a reaction. It's an annihilation. The source material is very vivid about this. When that intense, changing magnetic field hits all the conductive material on Earth, our power grids, our cables, pipelines,
What happens?
it induces these colossal electrical currents. It's basically a massive electromagnetic pulse, an EMP, but on a cosmic scale.
Okay, so break that down. What's the first thing to go?
First, your satellites, they're bombarded, the electronics are fried, they're either disabled or just shut down permanently, gone.
And then the grid on Earth.
Instantly overloaded. We're not talking about a blackout. We're talking about transformers literally melting, power flows reversing. The entire global grid is wiped out in a second.
And our devices, phones, computers.
If they're not protected, they die instantly, even if they're turned off. The induced voltage is just too high.
So a global instantaneous dark age. And this is just from proximity, no impact.
Just proximity. We have absolutely no defense for something like that.
And all of this is happening while the gravity is, as you said, having its say.
Right. Even if the magnetic field were somehow weaker, the gravity alone is strong enough to physically deform the Earth. The tidal forces are immense.
We think of tides as, oceans.
Yeah.
So planet-sized tsunamis.
Oh, absolutely. But it's more than that. The force is strong enough to affect the solid crust of the planet.
It would stretch the rock.
Exactly. The side of the Earth facing the star is pulled so much more strongly than the far side. You're literally stretching and squeezing the planet like taffy.
Which would cause?
Global, immediate, catastrophic earthquakes, volcanoes. The planet itself is torn apart from the inside out long, long before any physical impact.
And the sources say it can get even worse. There's an escalation factor. Rotation.
Right. So if this small, super dense hypermagnetic object is also spinning, we call it a pulsar.
A pulsar.
And a pulsar basically turns the neutron star into a focused energy weapon. Well, the star's magnetic axis usually doesn't line up with its rotation axis. So as it spins, it shoots out these focused beams of energy and radiation from its poles. It's like a cosmic lighthouse.
A lighthouse beam sweeping through space. What happens if that beam sweeps over Earth?
The energy output is just staggering. The sources quantify it. A single pulse from one of these powerful pulsars can be equivalent to the energy of billions of nuclear bombs exploding at once.
Billions.
And these pulses are happening over and over very rapidly. If Earth is in the path of that beam for any real amount of time, the radiation would just sterilize the surface. Instantly uninhabitable.
So we've got the gravity warping space, the magnetic field killing our tech, and now lethal radiation beams. If this thing is on a direct collision course, is there a term for what happens?
There is. Scientists use a pretty chilling term for it, actually. They call the area around it the kill zone.
They actually call it the kill zone.
Yes. And that zone is defined by the magnetic field that precedes the star itself.
So how does that work? What does it do?
The field is so disruptive, it acts like a cosmic bulldozer. As the neutron star gets closer, the field just it clears the space ahead of it. It strips away gas. It shreds dust clouds. It creates an environment so saturated with magnetism and radiation that nothing can exist in it.
So it's not even about the object itself arriving.
No, the physical object is just following in the wake of its own destruction. The destruction is a wave that hits you first, an environment where, basic chemistry and structure just can't be maintained.
Given all of this, this is absolute catastrophic potential. We have to ask the question for everyone listening. How would we know? Is there any warning at all?
There is a theoretical warning system, and it comes down to gravitational waves.
The ripples in space-time.
Exactly. An object this massive moving through space creates powerful ripples that our instruments, like LIGO, can detect. The strength of those waves is our siren.
Can we put that into stages? Like, what's the timeline from the first little warning to the end?
Based on the models, yeah, you can think of it as a 3-stage warning. The first stage would be a slight vibration.
And how far out would it be then?
Still very far, maybe out in the Oort cloud. That could give us months, maybe even a couple of years of notice, depending on how fast it's moving.
Okay, that's not a lot of time, but it's something, at least to prepare.
Potentially. The second wave would be significantly stronger. That signals it's entered the inner solar system, so past Neptune's orbit. At that point, the effects are starting to become measurable, and we'd know the catastrophe is probably happening.
And the third wave. The final alert.
The third and strongest wave means it's close, probably inside Jupiter's orbit. That's the point where its gravity and magnetic field are starting to really disrupt our whole solar system. The kill zone we talked about is starting to form.
And the time between stage 2 and stage 3.
That's the problem. At the speeds these things travel, it could be weeks or even days, not months.
That speed is the real catch, isn't it? We might be able to detect it, but if it's moving too fast, the warning doesn't really help.
That is the velocity problem. It's what scientists are really wrestling with. Neutron stars move at unbelievable speeds.
Why so fast?
The supernova that creates them is often asymmetrical, so it gives the star a huge kick. It turns them into these runaway stars just hurtling through the galaxy at hundreds of kilometers per second.
Hundreds. For context, Earth orbits the sun at about 30 kilometers per second.
So you're talking about an object moving, yeah, maybe 30 times faster than our own planet.
Wow.
And that speed, combined with the fact that they're dark, they're tiny, they're incredibly hard to track. One could suddenly pop out from behind a dust cloud or
Yeah.
just be lost in the background of the galaxy, and we'd only see it when it's effectively too late.
This whole conversation just it underlines the nature of cosmic power, doesn't it? We started with an object smaller than a city,
Mm-hmm.
and we've mapped out how it can melt our grid, warp our planet's crust, and kill everything electronic all before it even gets here.
It forces us to redefine what violent even means in the cosmos. The sources really suggest that these fundamental forces, when they're amplified to these extremes, are so much more devastating than just a collision.
An approaching neutron star is the embodiment of that.
The pure violence of physics itself.
So as we close out this deep dive, the final takeaway is that the destruction doesn't depend on impact. It's a certainty, just based on proximity.
Exactly. It's driven by that massive concentration of gravity and magnetism. We have to acknowledge the scale of energy that's possible in the universe.
And it leaves you with a pretty big question.
It does. We're always thinking about defending against, kinetic threats like asteroids, but we've seen today that the field effects are the real killers here. So the question to think about is this. If field-based destruction is the main threat from objects like this, what astronomical phenomena beyond a direct collision are we currently the least prepared to defend ourselves against?
What can we do when you're facing the raw power of nature's fundamental laws?
What can anyone do?
A truly chilling thought. Thanks for diving deep with us into the cosmic nightmare of the neutron star.